Welcome to my video course on engineering FRMCS. Today, we're mapping the exact evolution path from our current 4G evolved packet system straight into a 5G standalone architecture. We're going to explore how to upgrade physical hardware and transition network interfaces to really unlock next-generation rail operations.
Here's the agenda for today's explainer. We'll hit the FRMCS evolution blueprint, prepare hardware for upgrades, transition the control plane, modify user plane interfaces, and lay out the 5G standalone path. We're moving linearly from high-level hardware preparation directly into the granular architectural shifts of those control and user planes.
Section 1. The FRMCS Evolution Blueprint. Let's kick things off by establishing the foundational strategy for this massive transition.
So, we're currently operating within a critical transition phase known as FMRCST. And here is the good news. Because our existing 4G architecture is already all IP-based, it actually shares a ton of structural DNA with 5G. This gives us a massive head start in implementing mission-critical services like push-to-talk and live video across the rail network. We aren't starting from scratch here, and frankly, that's a huge operational advantage.
Section 2. Preparing hardware for upgrades. Let's tackle our first major engineering hurdle, getting both the physical and digital hardware ready for the leap.
Because of that IP-based foundation I just mentioned, preparing the hardware is actually highly efficient. Many commercial network devices out there only require a simple software update. Upgrading the core network is largely a digital exercise, saving us immense time and cost. However, the user equipment on the trains themselves, the mobile terminals and chips, those must undergo physical hardware module swaps to actually interface with the new 5G radio spectrum.
Think about how this functions in the real world. You've got central compute sites hosting the critical management functions, and they connect via miles of trackside fiber to edge compute sites that handle the actual user data. This entire interconnected web forms a backbone that can be upgraded to 5G standalone primarily through seamless software pushes. It's an incredibly elegant way to modernize infrastructure without ripping out thousands of miles of cables.
Section 3. Transitioning the control plane. With the hardware baseline set, we now need to drill down into the mechanics of the control plane, where the core signaling actually happens.
Right at the edge of the 5G core domain, we have our transport access points, specifically the TAP service agent. You can think of these as the vital translators. They sit directly between the transport layer, doing the heavy lifting below, and the service layer running the applications above, ensuring flawless interaction. They are completely responsible for routing that crucial signaling traffic.
Now, to make 5G really work, we have to modify our reference interfaces. We are mapping the legacy 4G RX interface directly over to its 5G equivalent, the N5, or N33 if a network exposure function is active. Transforming this specific reference point is absolutely crucial. It's essentially the green light for the secure, ultra-low latency signaling that modern automated trains require.
Section 4. Modifying user plane interfaces. Beyond control signaling, we also have to overhaul the actual data transmission pathways within the user plane. Just like the control plane, the user plane demands a strict architectural shift. We are replacing the 4G SGI reference point exclusively with the 5G N6 reference point. Sitting right at the edge of the 5G core domain, this new interface ensures our network can seamlessly hand off IP packets to external railway applications without hitting any of those legacy 4G bottlenecks.
The system architecture brilliantly details where those modified N5 and N6 interfaces function. They form the definitive boundary between the transport stratum down below and the railway applications up above. If these interfaces aren't correctly mapped to 5G standards, the media and signaling patchways break down and the onboard train applications simply go dark. Getting this right is completely non-negotiable.
Section 5. The 5G standalone path. Let's synthesize all of these engineering requirements into our final deployment blueprint moving forward.
This step-by-step pipeline must be followed precisely. Step 1. Execute physical radio module upgrades for the terminals. Step 2. Deploy those widespread software updates to the 4G all-IP network devices. And Step 3. Transform the control and user plane reference interfaces from RX to N5 and SGI to N6. By isolating physical upgrades and maximizing software flexibility, we create a highly efficient rollout strategy. With the 4G all-IP foundation minimizing core hardware swaps, how rapidly can railway infrastructure actually scale? once those N5 and N6 interfaces are fully active. Consider how this heavily software-driven transition completely accelerates our deployment timelines moving forward. Thanks, we can see you in next video.